Hello students, welcome all to another video of our engineering physics series where we will discuss about Heisenberg's uncertainty principle. Okay. So first here the statement is written, you can see it is impossible, it states that it is impossible to measure both position and momentum of particle accurately at the same time. If we measure the position at the same time, the particle will start moving. If the particle is in motion, it will start moving during that section, or during that fraction of second its position will be slightly changed. If delta x is the error or uncertainty in position and delta p is the error or uncertainty in momentum, then according to Heisenberg uncertainty principle, delta x into delta p equal to h. This is known as Heisenberg's uncertainty principle. We cannot measure accurately, simultaneously we cannot measure both position and momentum. So delta x is the error or uncertainty in position measurement, delta p is the uncertainty in momentum, then which is equal to h. Similarly, there are two other uncertainty principles are also there. One is between energy and time, which is equal to h. One is angular momentum L and angular displacement h. This is uncertainty principle, but experimentally it has been found that the minimum value is h by 4 pi, or which is equal to h cross by 2, where h cross equal to h by 2 pi. This is another constant. So you can also write down delta x into delta p is greater than equal to h cross by 2. This is the minimum value. Whenever there will be any numerical to calculate uncertainty in position or uncertainty in momentum, or similarly between energy, time, angular momentum or angle, you have to use this value because this is the experimental value which has been found, which is equal to h by 4 pi or h cross. H cross just symbolic representation of another constant which is equal to h by 2 pi. Now we are going to derive the expression delta x into delta p equal to h. We have to derive that. So in order to derive, we consider two simple harmonic waves. One is y1, another one is y2. Y1 and Y2 are two simple harmonic waves which are having same amplitude. Amplitude are same, but the frequency, propagation constant, all are slightly different. Let Y1 equal to A sine omega 1t minus k1x. Similarly, Y2 equal to A sine omega 2t minus k2x. A, you can see A is the amplitude of both the waves, which is constant for both, and omega 1 and omega 2 are the angular frequencies of first and second. Similarly, k1 and k2 are the propagation constant, that is equal to pi by lambda, because phi equal to kx, k is propagation constant, 2 pi by lambda, one is k1, other is k2. So the difference are very small. Now the resultant will be, let y equal to y1 plus y2. We have to just add here. In place of y1 we can write down a sine omega 1t minus k1x. In place of y2 we can write down a sine omega 2t minus k2x. If we take a common, we can write down like this. So this is in the form of sine c plus sine d formula. So sine, if this term, this whole term is, let c, this whole term is behave like c and d. So sine c plus sine d formula, sine c plus sine d formula is 2 sine c plus d by 2 into cos c minus d by 2. So we have to use that. So we get y equal to a, and sine c plus sine d formula is 2. So we have to multiply 2, then sine c plus d by 2. C plus means omega 1t minus k1x, omega 1t minus k1x. C plus d is omega 2t minus k2x whole divided by 2. C plus d by 2 into cos c minus d by 2. C minus means omega 1t minus k1x minus k1x minus this whole term. So this will be minus omega 2t, and this minus minus will be plus k2x divided by 2. This is just sin C plus sin D formula. Now we have to just rearrange that equation. This is equal to y equal to 2 times of a, that is there 2a. Here we can write down sin C omega 1 t omega 2 t. We can take t common, so this will be omega 1 plus omega 2 whole into t by 2, omega 1 plus omega 2 whole into t by 2 minus k1 plus k2. If we take minus sign outside, k1 plus k2 by 2 into x. This is sine term. Now cos term is also there, into cos omega 1 minus omega 2, here plus, here minus, omega 1 minus omega 2 by 2 into t. Again here also you can see minus k1x plus k2x. If we take negative sign, minus k1 minus k2 by 2 into x. This is the whole term. 2a sin omega 1 plus omega 2 by 2. Omega 1 plus omega 2 by 2 is nothing but the average value. So we can directly write y equal to 2a sin omega t. Omega 1 plus omega 2 by 2 is the average value. So average value is let omega t minus k1 plus k2 by 2 is the average value minus kx into cos term is there. Cos term is omega 1 minus omega 2, that is difference. So delta omega t by 2, delta omega t by 2 minus delta k x by 2. Here you can see delta 1 omega 1 minus omega 2 difference is delta. Similarly k1 minus k2 difference is delta k. That is I am writing here where omega equal to, this is the average value, omega 1 plus omega 2 by 2, k equal to k1 plus k2 by 2, delta omega equal to difference omega 1 minus omega 2, delta k equal to k1 minus k2. These are the difference. Now you can see the formula is in the form of y equal to 2a sin omega t minus kx into cos. We are considering simple harmonic wave. So the basic formula for simple harmonic wave is y equal to r sin omega t minus kx. So if we compare these two equations, equation number 1 and equation number 2, if we compare both of them, always simple harmonic wave is represented by wave equal to amplitude into sin omega t minus kx. So here except sin omega t minus x, whatever will be there, that is nothing but the amplitude. So if I compare equation number 1 and equation number 2, except sin omega t minus kx, whatever present here is the amplitude of the wave. So amplitude is nothing but, amplitude is here 2a, except this term whatever is there, that is amplitude 2a into cos, 2a into cos delta omega t by 2 minus delta kx by 2. This is the amplitude of the resultant wave. So do you remember node and antinode? Node and antinode. Node is this point. Node means where amplitude is 0. Antinode means where amplitude is maximum. So at node, both the amplitude of the resultant wave must be 0. So we have to use that condition. Here this is the amplitude. We have to use this must be equal to 0. At node, amplitude 0, so amplitude is here 2a, that cos term delta omega t by 2 minus delta k x by 2 equal to 0. 2a never be 0, so cos delta omega t by 2 minus delta k x by 2 equal to 0. cos theta is 0 means theta must be equal to some odd multiple of pi by 2. So delta omega t by 2 minus delta kx by 2 must be equal to 2n plus 1 by pi by 2. So directly you can write down 2n plus 1 into pi by 2. Now you can cancel 2 on both sides. So you get delta omega t minus delta kx equal to 2n plus 1 pi. Equation number 3. So this is a relation with change in frequency, change in propagation constant, which is equal to 2n plus 1 pi. Now if we write this equation for n equal to n and n plus 1, we get the equation delta omega t delta kx equal to 2n plus 1 pi. For nth position, we can directly write down delta omega t minus delta k, let xn equal to 2n plus 1 pi. Now for n plus 1th position, we can write down delta omega t minus delta k x n plus 1. In place of n, if we put n plus 1, this will be 2 into n plus 1 into 1. So this will be 2n plus 3, because 2 into 1 will be 2 plus 1 will be 3. This will be the result. So here you can write down 2n plus 3 pi. Now equation number 4, equation number 5. If we subtract 4 from 5, if we subtract them, equation 5 minus equation 4, if we subtract delta omega t will be cancelled, and this will be x n plus 1 minus x n into delta k. We take magnitude, okay? We are taking magnitude here. This will be 2n plus 3 minus 2n minus 1 into pi. We are taking magnitude, otherwise there will be negative sign. So this will be 2n minus 2n, 3 minus 1 is 2 pi. Directly you can write down. So here we get delta k. I am writing here delta k into x n plus 1 minus xn equal to 2 pi. This is nothing but the difference between n plus 1 and nth position, which is equal to the error or the uncertainty. So delta x equal to 2 pi by delta k. We get a formula here. But already we use the formula k equal to 2 pi by lambda. And from de Broglie wavelength, we know that lambda equal to h by p. So if we use that 2 pi by lambda is nothing but h by p. So we can use k equal to 2 pi p by h. Here you can see k equal to 2 pi by lambda equal to h by p cross multiplication 2 pi by p into h. Now delta k, change in k will be 2 pi by h is a constant quantity into delta p. Now we can use that in here. We can use that here, delta x equal to 2 pi by delta k. Now we can use. We have delta x equal to 2 pi by delta k. So 2 pi in place of delta k, we can write down 2 pi by h delta p. Now we can cancel 2 pi. This is h by delta p. So delta x equal to h by delta p or delta x into delta p equal to h. So this is Heisenberg's uncertainty principle in position and time. Similarly, you can also derive the uncertainty principle between energy and time. That is delta E into delta T equal to h. Kinetic energy, we know that kinetic energy equal to half m v square. In terms of momentum, we can write down p square by 2m. So change in energy will be just derivative 2p delta p by 2m. 2 we can cancel, p delta P by m. But what is P? Mass into velocity. So P by m, we have P by m. P by m equal to velocity. We can use that here in P by m. So this is called V delta P. So we get delta E equal to V into delta P. But velocity is rate of change of displacement dx by dt. So in terms of uncertainty, we can write on delta x by delta t. Once we use that here, V formula here, we will get the equation. So we have delta E equal to V into delta P. So in place of V, we can write down delta x by delta t into delta P. If we cross multiply, delta E into delta t equal to delta x into delta P. Delta x into delta P already we derived, which is equal to h. So we can directly write down delta E into delta t equal to h, which is the uncertainty between energy and time. This is all about Heisenberg's uncertainty principle. These derivations are important. Just practice, and if you face any problem, let me know in the comment section. Thank you.